Welcome. Today, we are looking at chemical equilibrium at an advanced level. This is a key topic in your chemistry exams for SS3. Pay close attention. Let us begin. First, let me review what chemical equilibrium is. Chemical equilibrium is the state in which the concentrations of reactants and products remain constant over time. It occurs in reversible reactions. A reversible reaction is a reaction that can proceed in both directions. The forward reaction converts reactants into products. The reverse reaction converts products back into reactants. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. The concentrations do not change. However, the reaction has not stopped. Both forward and reverse reactions are still occurring. They are occurring at the same rate. This is called dynamic equilibrium. Dynamic equilibrium is important in many chemical and biological systems. Now let me explain the equilibrium constant in detail. The equilibrium constant is a number that expresses the ratio of products to reactants at equilibrium. For a general reaction AA plus BB CC plus DD, the equilibrium constant expression is Kc equals concentration of C raised to the power of C times concentration of D raised to the power of D, divided by concentration of A raised to the power of A times concentration of B raised to the power of B. Kc is the equilibrium constant in terms of concentration. The value of Kc indicates the position of equilibrium. If Kc is very large, the equilibrium lies to the right. The products are favored. If Kc is very small, the equilibrium lies to the left. The reactants are favored. If Kc is around 1, the equilibrium lies in the middle. Both reactants and products are present in significant amounts. The equilibrium constant depends on temperature. It changes with temperature. It does not depend on concentration or pressure. The value of Kc is constant at a given temperature. For gaseous reactions, the equilibrium constant can be expressed in terms of partial pressures. This is Kp. Kp is related to Kc. By the equation, Kp equals Kc times RT raised to the power of delta N. Delta N is the change in the number of moles of gas. Now let me explain Le Chatelier's principle in detail. Le Chatelier's principle states that if a system at equilibrium is subjected to a change, the system will shift to counteract that change. The system will adjust to minimize the effect of the change. This principle is very useful for predicting the effect of changes in concentration, pressure, and temperature. It is used in industry to maximize the yield of products. Le Chatelier's principle applies to all equilibrium systems. The effect of concentration changes is that increasing the concentration of a reactant shifts the equilibrium to the right. Decreasing the concentration of a product shifts the equilibrium to the right. Increasing the concentration of a product shifts the equilibrium to the left. Decreasing the concentration of a reactant shifts the equilibrium to the left. The effect of pressure changes is that increasing pressure shifts the equilibrium to the side with fewer moles of gas. Decreasing pressure shifts the equilibrium to the side with more moles of gas. The effect of temperature changes is that increasing temperature shifts the equilibrium in the endothermic direction. Decreasing temperature shifts the equilibrium in the exothermic direction. A catalyst does not affect the position of equilibrium. It only speeds up the rate at which equilibrium is reached. Now let me explain the equilibrium constant calculations. Equilibrium constant calculations involve determining the value of Kc or Kp from equilibrium concentrations or partial pressures. The first step is to write the balanced equation. The second step is to write the equilibrium constant expression. The third step is to substitute the equilibrium concentrations into the expression. The fourth step is to calculate the value of Kc. For example, for the reaction H2 plus I2 2HI, the equilibrium constant expression is Kc equals concentration of Hi squared divided by concentration of H2 times concentration of I2. If the equilibrium concentrations are H2 equals 0.1 moles per cubic decimeter, I2 equals 0.1 moles per cubic decimeter, and HI equals 0.2 moles per cubic decimeter, then Kc equals 0.2 squared divided by 0.1 times 0.1. This gives 0.04 divided by 0.01. The result is 4. The equilibrium constant is quatra. Equilibrium constant calculations are important for predicting the extent of reactions. Now let me explain the reaction quotient. The reaction quotient is a quantity that tells the direction of a reaction. It has the same form as the equilibrium constant, but it is calculated using initial concentrations, not equilibrium concentrations. The reaction quotient is Q. If Q is less than Kc, the reaction proceeds forward. More products are formed. If Q is greater than Kc, the reaction proceeds backward. More reactants are formed. If Q is equal to Kc, the reaction is at equilibrium. The reaction quotient is useful for predicting the direction of a reaction. It is used in many applications. Now let me explain the ICE table. The ICE table is a tool used to calculate equilibrium concentrations. ICE stands for initial, change, and equilibrium. The initial concentrations are the starting concentrations. The change is the change in concentration as the reaction proceeds. The equilibrium concentrations are the final concentrations. The ICE table is used to solve equilibrium problems. For example, for the reaction H2 plus I2 to HI, if the initial concentrations of H2 and I2 are both 1 moles per cubic decimeter and the equilibrium constant is 4, the ICE table can be used to find the equilibrium concentrations. The initial concentrations are H2 equals 1, I2 equals 1, and HI equals 0. The change is x for H2 and I2, and plus 2x for HI. The equilibrium concentrations are H2 equals 1x, I2 equals 1x, and HI equals 2x. The equilibrium constant expression is 4 equals 2x squared divided by 1x times 1x. Solving for x gives the equilibrium concentrations. The ICE table is a powerful tool for equilibrium calculations. Now, let me explain the industrial applications of Le Chatelier's principle. Le Chatelier's principle is used in many industrial processes. The Haber process produces ammonia. The reaction is N2 plus 3H2 to NH3. The forward reaction is exothermic. High pressure favors the forward reaction. Low temperature favors the forward reaction. However, low temperature slows the reaction. A catalyst is used to speed it up. The process operates at high pressure and moderate temperature. The contact process produces sulfuric acid. The reaction is 2SO2 plus O22SO3. The forward reaction is exothermic. Low temperature favors the forward reaction. High pressure favors the forward reaction. However, the reaction is already at high pressure because of the gas volumes. A catalyst is used. The process operates at moderate temperature. The Haber process and the contact process are examples of the application of Le Chatelier's principle. Now let me explain the concept of equilibrium in biological systems. Equilibrium is important in many biological systems. The pH of blood is maintained by equilibrium. The carbonic acid bicarbonate buffer system maintains pH. The equilibrium is co-du pu du O du cotre H pu H key O tray. The buffer system resists changes in pH. Hemoglobin binds oxygen in the lungs. It releases oxygen in the tissues. This is an equilibrium. The binding of oxygen to hemoglobin is affected by pH and temperature. Enzymes catalyze reactions. They do not affect the position of equilibrium. They only speed up the rate. Equilibrium is essential for life. A common exam question asks you to write the equilibrium constant expression for a reaction. Here is a sample answer. For the reaction AA plus BBCC plus DD, the equilibrium constant expression is Kc equals C, C, D, D, A, B, B. The concentrations are equilibrium concentrations. The exponents are the stoichiometric coefficients. Kc is constant at a given temperature. It changes with temperature. It does not depend on concentration or pressure. Another exam question asks you to apply Le Chatelier's principle. Here is your answer. Le Chatelier's principle states that if a system at equilibrium is subjected to a change, the system will shift to counteract that change. Increasing concentration of a reactant shifts equilibrium to the right. Decreasing concentration of a product shifts equilibrium to the right. Increasing pressure shifts equilibrium to the side with fewer gas moles. Increasing temperature shifts equilibrium in the endothermic direction. A catalyst does not affect the equilibrium position. Another exam question asks you to calculate the equilibrium constant from equilibrium concentrations. Here is your answer. First, write the balanced equation. Second, write the equilibrium constant expression. Third, substitute the equilibrium concentrations. Fourth, calculate the value of Kc. For example, for the reaction H2 plus I22HI, if the equilibrium concentrations are H2 equals 0.1, I2 equals 0.1, and HI equals 0.2, then Kc gleich 0,2. 2 geteilt durch 0,1 mal 0,1 gleich 4. The equilibrium constant is quarter. Let me give you a quick summary. Chemical equilibrium occurs when the rates of forward and reverse reactions are equal. The equilibrium constant expresses the ratio of products to reactants. Le Chatelier's principle predicts the effect of changes in concentration, pressure, and temperature. Equilibrium constant calculations use the equilibrium constant expression. The reaction quotient predicts the direction of a reaction. The ICE table is used to calculate equilibrium concentrations. Le Chatelier's principle is used in industry. Equilibrium is important in biological systems. Practice these concepts. When you have them down, move to topic 4.